In this lecture, we're going to learn how to write the electronic configuration for atoms and ions, taking into account the new level of detail we now have about all the different electron orbitals within an atom. The learning outcomes for this lecture are firstly, you should be able to state Hund's rule, the Aufbau principle, and the Pauli exclusion principle, and use them to determine the electronic configurations of both atoms and ions. And secondly, you should be able to use both spectroscopic and box notations to write these electronic configurations. So, with all this choice, where does an electron go? Well, to explain this, we have to discuss three different rules. They are the Aufbau principle, the Pauli exclusion principle, and Hund's rule. So we'll start off with the Aufbau principle, which kind of works in the same way that our old ideas of filling electron orbitals. So the Aufbau principle states that the lowest energy levels are filled first. Now, the way to remember the order of filling the orbitals is through a diagram, and you should be able to reproduce this diagram in an exam. So if you remember, in the first energy level, we've just got an s orbital. In the second, we've got an S and a P. In the third, we've got an S, P and D. And in the fourth, we've got 4S, 4P, 4D and 4F. And so on for all subsequent energy levels. There are S, P, D and F. Now, the order in which they are filled goes like this. If we draw diagonal lines, we get the 1s orbital is filled first, then the 2s, then the 2p, then the 3s, then the 3p, then the 4s, then the 3d, 4b, 5s, etc. It would be unusual for you have to go beyond 5s orbital. So, the order of filling was 1s, then 2s, then 2p, then 3s, then 3p, then 4s, then 3d, etc. Now, you can try and remember that if you want, but I think it's better to remember how to construct this diagram in order to work out the order in which the electron orbitals are filled. So now we know what quantum numbers are, let's revisit the Pauli exclusion principle. So the Pauli exclusion principle states that no two electrons in the same atom can have the same set of all four quantum numbers. And the consequence of that is, if there are two electrons in an orbital, then the spins must be opposed. Let's take the lowest energy level, the 1s orbital. So one electron goes into the 1s orbital. It's got the quantum numbers 1, it's in the first energy level, 0, that's the number which represents an s orbital. The orientation is 0 for an s orbital, and it's got a spin of +1/2, which means it's spinning in a clockwise direction. When the second electron goes in there, it's 1, 0, 0. but it spins in the opposite direction. It's the anti-clockwise, so it's got a spin quantum number of -1/2. Now, you can't put another electron into that orbital because you'd have to have either that set or that set of quantum numbers. So that explains why only 2 electrons can go into any one orbital. So that justifies the fact that the total number of electrons which may occupy any one orbital is 2. Otherwise they would have the same 4 quantum numbers. So combining the Aufbau principle and the Pauli exclusion principle, we know that the first electrons will go into the 1s orbital. But that orbital can only take 2 electrons. So we write 1s, 2. The first 2 electrons will have these 4 quantum numbers. If we tried to put another electron into that orbital, we'd have to have one of these same set of quantum numbers, and that's not allowed. So the third electron would go into the next lower energy level, 2s, and once more that can only take 2 electrons, then it's full. After that, the electrons go into the 2p orbital. Now remember, there's 3 p orbitals. There's the px, the py, the pz. Each one can take 2 electrons, so the 2p can take up to 6 electrons. Once that's full, the electrons go into the 3s orbital, which can take 2 electrons. Then the 3p orbital, which can take 6 electrons. Then they go into the 4s orbital, which can take 2 electrons. Then they go into the 3d orbital. And d orbitals have 5 different orbital shapes, each one allowed to take 2 electrons, so we get a total of 10 electrons in the d orbitals. And so on. If we get to an f orbital, being 7 of them, that can take up to 14. Okay, so let's look at the first few elements and see what the electron configuration is. Well, if we start off with the first element, hydrogen, so you've got 1 electron and it goes into the 1s orbital. So it's got electron arrangement of 1s1. Helium with its 2 electrons is 1s2. Then we get lithium with its 3 electrons, so it's 1s2. Then it breaks into the second energy level and puts 1 electron there. Then we have beryllium, it's 4 electrons, so it's 1s2, 2s2. Then we have boron, it's 5 electrons, 1s2, 2s2, 2p1. Now the p orbitals, there's 3 orbitals, px, py, pz, but they call them degenerate orbitals, meaning that all 3 p orbitals are at the exact same energy level. So that 1 electron is as likely going to the px as the py or the pz. We can't actually say what one that's in. It could be the px, py, pz, because they're all at the same energy level. They're degenerate. When we get to carbon, it's then got 6 electrons, 2 go into the first 1s orbital, 2 into the second s orbital, and 2 into the 2p orbital. But the question is, what p orbital does that go into? Does it go into the one that already has an electron, or does it go into one of the others? Well, this is where our third and final rule comes in, Hund's rule. And Hund's rule states that when two electrons occupy degenerate orbitals, they do so in such a way as to maximise the number of parallel spins. One way of thinking of that is that electrons do not pair together until they have to. It's a bit like if you're on the mainland they get onto a bus, okay, and there's only one person sitting on the bus. It would be unusual for you to go and sit beside that person if you didn't know them. You'd go and sit in another seat, and that would continue until all the seats were filled up by one person, and it was only then that people start doubling up. So it's a bit like that with electrons. Okay, so our carbon atom is 1s2, 2s2, 2p2. So another way of representing that is in this way, which is called box notation. This is box notation. Whereas this is known as spectroscopic notation. We generally use spectroscopic notation more often than box notation because it's easier to write. But there's a few instances like here where you get extra information using box notation. So if you do the carbon atom with box notation, there's one electron in the 1s orbital, so it's got half an arrow pointing one direction to represent spin, and the second electron points in the other direction, representing it spinning in the other direction. So there's our two 1s orbitals. Then we've got two electrons in the 2s, then we've got two electrons in the 2p orbital. So there's what nitrogen looked like, but the sixth electron, so according to Hund's rule, it doesn't go into the same electron orbital. Okay. It goes into one of the other electron orbitals. It wouldn't go in like that because that's not maximising the number of parallel spins. They're spinning in the opposite directions. So it goes into one of the empty orbitals and spins in the same direction as the electron that's already occupying one of the p orbitals. So this box notation just gives you a slightly better description of what's happening with regards to Hund's rule. So if we look at the next few elements, so we've come up to carbon, so next one's nitrogen with 7 electrons. So it would be like that. So 1s2, 2s2, 2p3. Then after nitrogen we've got oxygen, so that's 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and now it has to start pairing up. 8. So it's 1s2, 2s2, 2p4. Then we have fluorine with its 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 1s2, 2s2, 2p5, and just to complete that period, we then have neon with its 10 electrons. And as you'd expect to be neon, it's got full energy levels, 1s2, 2s2, 2p6.